Hello everybody, thank you for joining me today. My name is Milam and today we're going to be looking at radiation and its risks. So our learning objectives are to understand the need for protection against radiation. So why do we actually need to be protected from it? To recall the difference between irradiation and contamination. That's a really key point because a lot of people get very confused between those two terms. And to state how we can minimize radiation exposure. So if you're ready for it, let's get right into it. Now let's have a look at actually detecting radiation. First thing that you need to know is that radiation doses, so doses of radiation, are measured in sieverts. So that's a brand new unit here, but you often only need to understand that the dose is measured in sieverts rather than having to really explain it. So dose of radiation is measured in sieverts, which has the symbol SV, and common doses are millisieverts. Okay, so a sievert is quite a big unit, so we really only use millisieverts to measure radiation doses. Okay, now there are two main ways that you need to understand of detecting radiation. One is called a dosimeter. Another, the more recognizable one, is called a Geiger counter. Let's have a look at a dosimeter first. So a dosimeter is just a badge worn by some people who are exposed or will be working with radiation, and that has photographic film on it. So that's this little circle. Oops, that's this little circle right here. So as the photographic film is exposed to radiation, most commonly gamma, it develops and changes color. So the darker the color of the photographic film, the longer or the more you've been exposed to radiation. So this gives you a very rough but quite accurate representation of how big of a dose you're getting by radiation, because the darker the color, the bigger the dose you'll have received. Okay, so the Geiger counter works by displaying counts per minute of radioactive particles being detected by the tube. Okay, so it's kind of intuitive, like the higher counts per second, the higher doses the higher the dose you're receiving. So now you understand the two main ways of detecting radiation. Okay, now let's have a look at why radiation is actually harmful. So I have here the chemical reaction between a free electron, which if we remember is just a beta particle, because a beta particle is a high-speed free electron, and a DNA and a piece of DNA, right? So what actually happens when the beta particle hits the DNA? So the beta particle collides with DNA molecule. The beta particles are ionizing. Now, if we go back to our definition of ionization, we remember that ionization is the process of removing electrons away from an atom. So beta particle ionizes the DNA molecule. So the DNA loses electrons. So now the shape of the DNA molecule has changed. And that leads to mutations. So mutations really occur when there's a breakage or a change in the actual DNA here. And here we can see that a beta particle, when it collides with a molecule of DNA, it strips electrons away. It actually changes the actual structure of DNA, mutating it, which is why radiation is harmful, because this mutation could then have a sort of domino effect and lead to a cancer growing. Now, I've given the example of a beta particle here, but this can also be the same case with alpha and also the same case with gamma as well. But there are some differences between the harmfulness of different radiation. So, outside of the body, actually let's just do it in green. Outside Oops. Outside of body. Outside of the body, which type of radiation do you think will be the most harmful? Well, that's actually gamma. That's because gamma is very penetrating, extremely penetrating. So it can go deep in body, right? So it can go deep into your body, and it can cause mutations way beyond just surface level of your skin. But then it's beta particles, beta, because they're moderately penetrating, Then it's alpha. That's because they're not very penetrating at all. Right, alpha particles can be stopped by a few centimeters of air, so that means that you can hold an alpha source in your hand and be sure that it's outside of the body, not going to really harm you at all, because the alpha particles can't even travel that big of a distance to actually get to your cells themselves. But when we look at inside of the body, so let's do that down here. I'm running out of space. Let's highlight these two so they're clear. Now, alpha particles are the most dangerous. Most danger. Well, why is that? That's because alpha particles are the biggest particle of ionizing radiation you have to learn about at GCSE. That means that they carry a lot of energy, albeit a very short range, but as soon as they're inside your body, they only have to travel a very short range to get to your cells, so they can wreak a lot of havoc straight away because of their very extreme, very big size, and so extreme ionization power. Then it's beta particles, moderate danger, and then surprisingly it's gamma. That's because they just pass right out of your body. Because they're so penetrating, they just penetrate your entire skin and they pass out straight into the earth, rather than wreaking havoc on the close range cells that are right in front of the gamma cells themselves. So now you understand why radiation is harmful and the levels of harmfulness of each of the three types of ionizing radiation outside of the body and inside of the body. Okay, so now let's have a look at irradiation versus contamination and safety precautions when working with radiation. So let's have a look at irradiation first. So irradiation just talks about the exposure to radioactive, can barely spell, material. Okay, so technically in real life, all of us are constantly being irradiated at all times, because remember earlier on I told you that everything around us, the food we eat, the air we breathe, the clothes we wear, are all very, very slightly radioactive. So really we're all technically always being exposed to some form of radiation, so we're being irradiated. But that's very different to contamination. Contamination is the unwanted presence of radioactive material. So that's things like dust, chips, things like that, right? So if there was a nuclear accident, right, and a nuclear reactor blew up, it would spew out all of its radioactive material out into the air in fine little particles, and that would contaminate the air. But say it was still say a piece fell right near you, right, without you touching it, you're still being irradiated because you're in the presence of radioactive material and the gamma rays from the material are being exposed to you, but you're not contaminated, because until you actually touch it or you breathe in some of the dust, and you get the dust on you, right, then you're contaminated, but otherwise you're not. So that's the difference between irradiation and contamination. Now let's have a look at the safety precautions when working with radiation, and these are directly related to both irradiation and contamination. So the first safety precaution is just time. So longer times lead to higher levels of irradiation, right? Because you're in the presence of radioactive material for longer, and also increase harm if contaminated. Right? So can you understand that, right? So if you are holding a piece of like contaminated or a piece of radioactive material, that's contaminating you, and the longer you hold it for, the more it's irradiating the whole of your body, and the more the contamination, the contaminated material is actually harming your body itself. So the first thing is time. So we always want to limit time in presence of radioactive material. Okay, so that's our first one. Then we have PPE, which stands for personal protection and equipment. So this could be things such as gas masks, gloves, overalls. Like you see in movies, there's people wearing, you know, big yellow suits. That's PPE, right? Personal protection equipment. Okay, so PPE prevents contamination because say any sort of radioactive material were to break off that you are using, right, it would fall on your gloved hands, or it would get stuck in the filter in your gas mask, and you as a person wouldn't actually breathe it in. So it prevents you being contaminated, but it does not prevent irradiation. Because remember, gamma and beta particles are beta particles are fairly penetrating, and gamma particles are very penetrating. So even if you're wearing PPE, so gloves and masks, those radioactive particles can still penetrate through that and still irradiate you. Okay, so you have to understand that. So another thing that you can do with PPE to limit both irradiation and contamination is, again, limit time in presence of radiation. So this is going to be a very common theme. You can also use a thicker and more, different materials of PPE, right? Because some PPE will be rated for beta particles, some will be rated for more gamma exposure. Now the final thing is called shielding. So this is the locking of radioactive particles through physical barriers. So this could be lead sheets, wooden boxes, and even plain old water. Water is an excellent material for shielding, which is why often nuclear test reactors are buried under massive pools of water, and the radiation doesn't even move past maybe a couple meters. So this is for the storage of radioactive material. So nuclear waste from nuclear reactors are actually packed tight into steel drums, which are then coated with a layer of bulletproof glass, which acts as a sort of shielding against all the types of radiation, even gamma, that is given off by the waste. So shielding is often used for the storage of radioactive materials. In fact, in your school, when you do experiments with radioactive material, you'll see that the source is often kept in a wooden box that's lead lined. So that prevents any sort of radiation leakage from the actual source itself. So now you understand irradiation versus contamination and safety precautions to use when working with radiation.